that's
missed
what I just,
fulminates, but I
yeah,
tell you,
fulminates are pretty bad.
I just didn't know much of anything.
Well, there you go.
My dad brought a book home
Yeah,
where he worked
yeah.
with basic chemistry, and then I started looking at their oxidizing agents.
Right, yeah.
Man.
The perchlorates.
Oh, oh, yeah.
Oh, yeah. Well, I am proud of the fact that I have read not to commit
I know it is. I would never have asked you that.
Nitric acid, sulfuric acid. But you have to be a bit careful in how you do it. But, yeah.
Well, yeah, you
Yeah.
gotta keep it
Yeah.
Hey, thank you all for coming this evening. We're all in for a treat. Professor Alex Filippenko was a member of the prestigious panel of Nobel Conference 49 in 2013, and we're happy that he's agreed to return this spring to engage our current students and to present 2 public lectures on his research. We begin this evening with the acknowledgement that Gustavus is located on the homelands of the Dakota people, whose spiritual traditions include the belief that this land, along with the creatures and people living on it, are their relatives. The Minnesota River, which passes through St. Peter, and its watershed are sacred places. These waters and lands are interconnected with Dakota culture, language, creation stories, and spiritual rites. In spite of traumatic history that includes forced removal and attempted extermination, Dakota people still live and practice their culture on these homelands today. We seek to honor our neighbors who are Dakota by learning more about our interrelated histories and through building relationships in order to co-create a better future for the people and creatures living within these ecosystems today. Before we begin tonight's lecture, I need to also acknowledge the very generous support of the Rydell family. The Rydell Professorship at Gustavus Adolphus College is a scholar-in-residence program designed to bring Nobel laureates and similarly distinguished scholars to the campus as catalysts to enhance learning and teaching. The Rydell Professorship was established in 1993 by Doctors Robert E. and Susan T. Rydell to give students the opportunity to learn from and interact with leading scholars. We are fortunate that Dr. Susan Rydell is with us tonight, along with President Rebecca Bergman and Vice President Tom Young up front here. Well, Tom's in the back, I guess. It is my pleasure this evening to introduce Dr. Alexi V Phillipinko. Dr. Filippenko is the Richard and Rhoda Goldman Distinguished Professor in Physical Sciences and a Miller Senior Fellow in the Miller Institute for Basic Research in Science at the University of California at Berkeley. His enormous number of accomplishments, documented in about 1,000 research papers, have been recognized by many major prizes, including a share of both the Gruber Cosmology Prize in 2007 and the Breakthrough Prize in Fundamental Physics in 2015. I could take several minutes to list all of his accolades, but would like instead to describe the physics department's excitement with his visit as Rydell Professor in a little story. In January of 2007, some of my colleagues and 2 students and I attended the 209th meeting of the American Astronomical Society in Seattle. The meeting was a joint meeting with the American Association of Physics Teachers, and the 2 students were presenting their summer research. Fortuitously, we were also able to attend many of the AAS talks, including ones by Professor Filippenko and several other Nobel Conference 49 panelists. In fact, it was at that meeting that we dreamed up the idea of the universe at its limits, the Nobel Conference 49. So it was very exciting when it came to pass in October of 2013 that Alex Filippenko and the other speakers brought that conference to life. One of the students who presented their research that January also caught the excitement of astrophysics and cosmology and pursued graduate work in astrophysics at the University of Minnesota. Danielle Berg happened to be teaching with us as a leave replacement in 2013 and hosted one of the other speakers for the Nobel Conference. Danielle is now Assistant Professor of Astronomy at UT Austin and helped seal the deal with Alex as this year's Rydell Professor when she gave a colloquium at Berkeley last fall. I tell this story as an illustration of the ability that Professor Filippenko has to get students of all ages excited about astrophysics and cosmology. He has won the most prestigious of teaching awards at Berkeley and has also been voted the best professor on campus a record 9 times. Owing to his popularity, he regularly teaches enormous classes in astronomy, but he also has found time to produce astronomy video courses with a great courses series co-author an award-winning astronomy textbook, and appear in more than 120 TV documentaries, including about 50 episodes of the Universe series. I hope this explains why we're so excited that Alex agreed to serve as this year's Rydell Professor. He has already met with several classes in physics and groups of students and conducted a tour of the universe using his personal telescope in our observatory last night. Tomorrow evening, he will present a more technical talk about Type 1a supernovae and the accelerating universe. But tonight, we're excited to hear about dark energy and the runaway universe. Please help me welcome Professor Filippenko to Gustavus.
Well, thank you very much for that kind introduction. It's certainly wonderful to be here again. I've enjoyed interacting with the students and the faculty in my first 2 days here, and I've got a couple more to go. As Chuck mentioned, I was at the Nobel Conference 49, and here are some photographs that Danielle Berg sent me late this afternoon when I realized that, hey, it'd be fun to show them. And she happens to be at an astronomical conference in Ireland, but she managed to get these to me before it was too late. So minutes before we went to dinner, I got these, and there we are. And in fact, there's Danielle picking me up from the airport, I guess, and then taking me to one of the guest houses. I don't remember which one I stayed at, but anyway, here we are, all kind of yupping it up after, I don't know, whether we were at some happy place or a bar or something. I don't know where we were, but anyway, that was certainly a lot of fun, and I think it's fantastic that Gustavus has this program and does a conference of this sort every year. It's a great way to introduce students to leading scientists in a variety of fields. So today I'll be discussing cosmology. Now, cosmology is that subset of astronomy that deals with the structure and evolution of the universe as a whole. We're interested in really some of the grandest topics imaginable. Fundamentally, where the hell did it all come from, right? This is what cave people have been wondering about since thousands of years ago. And here we are millennia later, and we're still wondering the same things. Where the hell did it all come from? Or at least, how did it evolve? And specifically, some of these questions within cosmology are, when did the universe begin? You know, it actually, we think, is not infinitely old. It's 13 or 14 billion years old, but it could have been infinitely old. You can see this is a big time story, right? When did the universe begin? And you know, these magazines, they're to present the news and to educate the public, but they don't sell only through subscriptions. They sell newsstand issues as well, and they won't choose a cover story that they don't think will sell, but astronomy, and in particular cosmology, sells. So when did the universe begin? And here's another one, how the universe will end. Well, this was written 20 years ago about our group's work. Back then, we thought we knew how the universe would end. Now we've done a little bit more research, and as I'll tell you, we're not quite so sure that we know how the universe will end, but we can lay odds. Anyway, there should have been a question mark here, or how will the universe end? Peering deep into space and time, scientists have just solved the biggest mystery in the cosmos. Anyway, we're not sure of the exact fate, but I'll tell you of the possible fates today. We're also interested in giant collections of stars called galaxies. Now, we live in such a collection, the Milky Way galaxy, 100 billion or more stars gravitationally bound together, 100,000 light years across. Now, a light year is 6 million miles, you know, so these things are gargantuan systems. Our spiral galaxy would look something like this if we could view it from the outside. This is a different one. We're viewing our galaxy from the inside. We're like a mouse within the maze, so we don't have a very clear view of it. If someone has a picture of the Milky Way that looks like this, come see me afterwards. I'd like to purchase usage rights from you or something, you know. But anyway, we think through studies of our own galaxy. It looks something like this. And there are lots of these things, okay? You know, you look at something like the Hubble Space Telescope Ultra Deep Field. which is just a small but representative part of the sky. How small? Well, imagine a grain of sand held at arm's length. Imagine how small that looks. That's the fraction of the sky shown here. And everywhere it's filled with galaxies. I can count them. 1, 2, 3, 4, 5. Yeah, I could use up my 50 minutes counting galaxies. That would be pretty boring for you, but you know what? It's a rather cushy job. They pay me to sit around and count galaxies. I have to pinch myself. How could I be so lucky? Anyway, there are thousands of them in this grain of sand, and it is representative. We've taken many such photographs of different parts of the sky, and statistically they all look the same. So within the realm of what we call the observable universe, there's more than 100 billion galaxies, each with billions of stars. And that's just in the parts of the universe that we can see. We now have good reasons to believe that the universe extends far beyond those parts that we can see. So how did galaxies form? How do they evolve? These basic building blocks of the universe. These are also some of the key questions of cosmology. So I feel very, very fortunate indeed to be privileged to work in this wonderful, wonderful field. Well, to go back to the beginnings of cosmology, let's give due credit to Vesto Slipher, someone who's not well known. He worked at the Lowell Observatory near Flagstaff, Arizona, about a century ago, and he examined what was then called the spiral nebulae. These were not known to be external galaxies. Some astronomers thought they might be external. Some thought they might be clouds of gas within our own galaxy. But he collected the light from these spiral nebulae and passed it through a prism or another such device, which spread the light out into a rainbow, a spectrum. And from the spectrum, you can tell all kinds of interesting things, like the types of gases that the stars that make up the galaxies are made of. You can see, hydrogen, neutral sodium, singly ionized calcium. A trained spectroscopist can recognize the patterns, almost like a fingerprint, okay? And this is how we know, by the way, that the stars are made out of the same 92 elements as those naturally occurring here on Earth. So Slipher saw the same patterns as in our own sun, for example, but shifted toward redder colors, longer wavelengths. And if interpreted as being caused by a motion, this implied that most, not all, but most of these spiral nebulae are moving away from us. But Slipher did not know the distances of the spiral nebulae, so he couldn't do much more with these data. Enter Edwin Hubble, much better known. With good reason. He did some good work, but he also did some work that did not properly credit the work of other astronomers, such as Vesto Slipher. He didn't reference Slipher's paper in his own paper, which would be grounds for removal even of a tenured professor from a university, right? If half your data were someone else's work and you did not reference it. But anyway, be that as it may, Hubble used the 100-inch Hooker telescope at Mount Wilson Observatory above the LA basin. And he looked at these spiral nebulae, in particular a very famous one, the Andromeda Nebula, M31. And he was specifically looking for stars that suddenly brighten by some pretty good factor, and then they fade for a few decades, and then they might brighten again. They're called novae, short for nova stella, new star. We now know they're not new stars, they're old stars that brighten by a large factor every once in a while. But then he noticed one here, marked with an N initially, where in previous photographs he could still see the star, and then it brightened, and then it faded, and then in other photographs it brightened again. So it was clearly a variable star, not a nova that might re-brighten every 10 or 20 or 30 years. And in particular, here's a photograph of that famous first one, taken with the Hubble Space Telescope. He saw that they have the pattern, the brightening and fading, of a very well-known type of variable star in our own Milky Way galaxy, something called a Cepheid variable. And these things typically brighten with the period and then fade again with between 1 and 100 days. They're not all the same, but they all have this relatively rapid rise and a more gradual decline. And these are very powerful stars. They are between about 110,000 times the oomph of our sun. So they could be seen to great distances, okay? And their true oomph was calibrated by Henrietta Swan Leavitt at Harvard College Observatory in 1912. So some characteristics of these stars were known, and if you know the true power of a star and you see another star that behaves just like it, for example, like a headlight, you look at a known headlight of known distance, it's 2 meters away, you say that's a bright headlight, and you make some other measurements and determine that it's a car headlight and not a bicycle headlight or some giant semi-truck or something like that. So it's a standard headlight. And then you look at it, it looks fainter if it's farther away, looks fainter still if it's even farther away. Well, the same thing with the Cepheid variables. You could compare their known oomph, their luminosity, with their apparent brightness and determine their distance. In the case of cars, your brain does this calculation pretty quickly, pretty intuitively. If you're not good at doing this quickly, you shouldn't be driving at night, okay? Plus, with a car, you have a consistency check. The nearby headlights have a larger angular separation than the more distant headlights. That's one reason it's harder to accurately judge the distance of a motorcyclist, because there's only one headlight. But anyway, stars, cars, it's the same idea. Find a star whose true properties, including its true power, look at how bright it appears to be, and thus determine the distance it needs to be at in order to appear that faint. So, in doing this for the Cepheid variables in the Andromeda Nebula, Hubble realized that this thing is about 1 million light years away. The modern value is 2.5 million light years. For technical reasons, he got slightly the wrong answer. But the gist of the argument was correct. It was way outside the reasonable extent of our Milky Way galaxy, which was the known universe back then. So now these spiral nebulae became external galaxies, island universes, as had been hypothesized by Immanuel Kant and others 200 years earlier. He figuratively expanded our view of the universe with this discovery. That was 1923, 1924. 5 years later, he did something related, but even more important, in a sense. He found that the galaxies whose spectra Slipher had measured and which showed only pretty fast motions away from us were relatively nearby. The galaxies that looked fainter and smaller in the sky, and thus reasonably were more distant, had bigger velocity shifts, bigger redshifts of the spectrum. So he found that redshift is proportional to distance, and all these things were sufficiently nearby that you could say that you're looking at them right now. So right now, the more distant the object is, the faster it's moving away from us. It's an expanding universe. Now, people flippantly say, everything's expanding. Well, wait a minute. What's expanding? Our Earth is not expanding. It's held together by its own gravity, okay, which greatly overcomes the tendency of empty space to expand. Our solar system is not expanding. It's held together by the sun's gravity. Our galaxy is not expanding. It's held together by the gravity of all the stuff in it. I'll mention some more about that stuff in a minute. Even clusters of galaxies like this. Now we're out to 1 million light year scale. They're not expanding. So I'm out to 1 million light years. So far nothing's expanding. So what are we talking about, an expanding universe? Well, when you reach, say, 10 million light years and beyond, that's a reasonable distance, and you look at like groups or clusters of galaxies there and there, or if you look at isolated galaxies, say 10 million light years apart from each other, then you find that the space between them is getting bigger, okay? The universe is expanding on large scales, not on small scales. So the galaxies here are deliberately shown as not expanding, but it's the coordinate system that's expanding. It's not that the galaxies are moving through some pre-existing space. We believe that it's the space itself that's expanding. There's a few cosmologists that disagree with that interpretation, but I say to them that in disagreeing with it, they're rejecting all of the general theory of relativity. So I just don't think they have a really good argument, even though, as they claim, mathematically, at least at small distances, it's hard to tell the difference between an expansion of space and a motion of objects through space, causing a Doppler effect, like the siren moving away from you. But no, we think the redshift, this tendency of the spectral lines to be at longer wavelengths, the cosmological redshift, is caused by the expansion of space itself. And things that are nailed down and bound to themselves or to Earth or whatever don't expand. But over very large distances, the space expands and the electromagnetic waves, the light permeating that space, expands. So that's the origin of the so-called cosmological redshift. Okay, so there's a lot of misconceptions about this, which you can find in cartoons and stuff. Sorry, I'm late, but you know how the universe keeps expanding. No, the next time you're late to work, you can't use that excuse, okay? If the universe and everything in it is expanding, how come our budget gets shrunk all the time, okay? The president of the college can probably appreciate that. Can't blame the expanding universe. All right. So with today's telescopes, we've measured the current rate, and it's some number. It's an interesting number. I'll get back to it at the end of my talk. But for now, I want to concentrate on how that number should change. And why? Well, that goes all the way back to Isaac Newton, who supposedly saw the apple fall from the tree and wondered whether whatever it is that's causing the apple to fall is the same as what's causing the moon to be in an orbit around Earth rather than flying off somewhere, okay? He tried to unite terrestrial and celestial phenomena, and he did so with his law of universal gravitation and his 3 laws of motion. The moon is falling toward Earth, it's just that it has some perpendicular motion as well, so it keeps on missing, okay? Well, all the galaxies should be pulling on each other, all right? These galaxies here should be pulling on those galaxies there, slowing down the expansion of the universe just as the apple slows down, right? And in fact, it's not just the visible matter in these galaxies that's pulling on the visible matter in the other galaxies. There's also a bunch of dark matter in galaxies and in clusters of galaxies. What is dark matter? Well, it was first proposed, although he didn't make a big deal out of it, by Fritz Zwicky, someone whom I greatly admire. In the 1930s at Caltech, and using the Palomar Observatory, he noticed that the various galaxies in a cluster like this were moving around so quickly that the cluster would rapidly fall apart if there were not additional gravity holding it together, additional in excess to the gravity that could be ascribed to the visible stars, all right? And this wasn't the only cluster. There were lots of clusters in the sky. So clearly these were not just chance superpositions of galaxies passing each other through the night. These were clearly real bound structures. Here's another one, a more modern picture with the Hubble Space Telescope, all right? So he proposed there might be dark matter there, holding them together. He was largely ignored by his colleagues. Most of them didn't like him very much. He was brilliant, but arrogant and abrasive. And he didn't think highly of the intellectual capabilities of his Caltech colleagues. And you know, Caltech is a pretty brainy place, and there's a lot of big egos there, and you know, they did not take kindly to his view of them. Here, he may be showing you what he thinks of the typical brain size of one of his colleagues. I don't know that that's what he's thinking, but it could be. He is on record as having referred to his colleagues as spherical bastards, because you know, they're bastards any way you look at them. And of course, a sphere is the only shape that looks the same from all directions. I'm not recommending you adopt his style, his approach to friendships. You will end up quickly friendless. But anyway, I admire Fritz Zwicky for many of his ideas. He was ignored for decades. Then along comes Vera Rubin, who studied the spiral galaxies with her colleagues in the 1970s. She found that spiral galaxies are rotating so quickly that they would go flying apart unless there were extra material holding them together. She was routinely ignored as well, but not for decades and decades the way Zwicky was. By now, and even 30 or 40 years ago, the study of dark matter has become one of the biggest subfields of astrophysics, okay? But the idea was ignored for at least 5 or 10 years. What is the dark matter? Well, that's not the main point of my talk. Could be a number of things. One idea is that it's black holes, right? It's regions of space where matter is compressed so much that nothing, not even light, can escape. However, there are ways we can show that black holes and other forms of dead stars can't be a majority of the dark matter. Only about 1/6 at best, and probably even much less than that. Some of it is hot gas that's just not very easily visible, but we have now found it. But most of it can't be made out of what we call normal matter, the stuff made out of protons and neutrons and electrons. Most of it has to be exotic. And one idea is that it's WIMPs, weakly interacting massive particles. This is to contrast them with dead stars, which are called machos, massive compact halo objects, okay? It's the WIMPs against the machos. So these are various particles that are left over from the Big Bang. They are not protons and neutrons and electrons. They don't interact through the usual electromagnetic interactions or what's called the strong nuclear interactions. They only interact through gravity and through what's called the weak interactions. And so they're hard to find because they just, one example of a weakly interacting particle, though not a massive one, is a neutrino. And if you go to Ace Hardware and you buy yourself a light year thickness of lead and you shine a neutrino beam through it, half of the neutrinos will make it through without having bounced off of anything at all. It's as though they're going through a vacuum. That's just an illustration of how weakly interacting the weak interaction is. So it's hard for physicists to find these things. They've been searching for 40 years now. They still haven't found them. I'm beginning to get mildly worried, but I'm not worried enough yet to completely, go back to the drawing board. Okay, so because of the visible matter and the dark matter, the universe should be slowing down. How much? Well, if the density of the universe, the mass per unit volume, is large there and in other places, then it'll be like the apple, tossed up, it slows down, comes to a stop, comes back. So you could say, in the case of the universe, Big Bang, Big Crunch, or Big Bang, Gnab Gib, which is Big Bang backwards. Write it down. Big Bang, Gnab Gib. So if I were living in that kind of a universe and I were lying on my back watching the galaxies, I would see them getting fainter and smaller, and I would say, ooh, I live in a well-behaved universe. But then I'd notice something rather peculiar. Right about now, I'd start getting kind of nervous, and then goodbye, cruel world, because the universe collapses in on itself in the Big Crunch, hot, dense, compressed. That's one possible ending for the universe. But the universe's density could also be sufficiently low that, yes, it slows down, but never comes to a stop, all right? Or barely comes to a stop. And so that would be like an apple launched at a speed greater than or equal to Earth's escape speed. If I had eaten my Wheaties this morning and there weren't the technical difficulty of a ceiling here, I could in principle do it. 11 kilometers per second, okay? That's what rockets do. So in that kind of a universe, you would see the galaxies growing fainter and smaller forever, all right? Cold, dark, dilute, a very different fate from the Big Crunch. We would like to know the fate of the universe. Why? Just because. It is a question of interest. Maybe it will lead to a better pacemaker. I doubt it, but you never know. And it's this kind of research that excites kids to get into STEM fields. Most won't become professional astrophysicists. That's okay, And plus, you can determine things about the universe that no other animals that we know of can. And it could be that Homo sapien type intelligence and mechanical ability is quite rare in our galaxy. I happen to think that for a number of reasons, but that's a different talk. How do we determine the fate? By looking at the past history of the expansion. If you measure the speed of this apple at many different times, and you measure that it's slowing down a lot, then you can calculate that it'll someday stop. If it's not slowing down a lot, then you could calculate that it'll keep on going forever. Well, we can measure the rate of expansion now. But how do we go back in time? By using light. Light travels about a foot per nanosecond. So I'm seeing Chuck here as he was maybe 12 nanoseconds, 12 billionths of a second ago. He may not even exist anymore. Oh, he does. Good for him. He's still in this good universe. You see the sun as it was about 8 1/3 minutes ago, because it takes 8 1/3 minutes to traverse 150 million kilometers. The nearest stars, the bright stars you see, are some tens or hundreds of light years away, in a few cases 1,000 or 2,000 light years. So you're seeing them as they were, tens or hundreds or a few thousand years ago. Look at galaxies that are 1 billion light years away, 4 billion light years away. Maybe that little blob there is 9 billion light years away. You're seeing them as they were 1, 4, 9 billion years ago. And encoded in the light, in the form of that redshift thing that I was talking about, is information about how much the universe has expanded during the time of flight. So we need to know the distances of these galaxies, thus the look-back times, and we also have to measure how much their spectrum has shifted. Well, how do we get the distances? Cepheid variables don't cut it for galaxies that are billions of light years away. Despite being up to 10,000 times as luminous as the sun, that's just not enough to be seen at distances of billions of light years. So what do we use? We use exploding stars. A small minority of stars go through a titanic act of self-destruction at the end of their lives, becoming millions or even billions of times more powerful than the sun. Here's one of these. Takes a couple of weeks to brighten, some months to fade. We sped up the process so as not to bore you. But notice that when it's at its maximum brilliance, it's about as bright as the central few billion stars in this galaxy of 100 billion. So that's one star, folks. Our sun won't do this, but if our sun were to do this, sunblock of 50 just wouldn't cut it. You'd need sunblock or supernova block of a few billion to protect yourself. But don't worry, be happy, it's not going to explode. If it does, you can ask my chancellor to fire me. The least of my worries will be the prospect of being fired from Berkeley if the sun explodes. The least of your worries will be getting me fired from Berkeley if the sun were to explode. So anyway, we find them in galaxies whose distances have been measured in a more conventional way, using Cepheid variables or other such distance markers. So here's a galaxy whose distance we know. We see how bright the supernova becomes. That's like the car of known distance. That allows you to calibrate how powerful the headlight is. Now go and do some cosmology. Find them in the distant galaxies, measure their brightness, figure out how far away they are, and thus how far back in time you are looking. That's the name of the game. So a supernova is used to measure the distance of a galaxy through the inverse square law and the galaxy's recession speed, this redshift thing. All right? That's the two things, actually, that the supernova gives you, both in one blow. Actually, it's great. So around 1990, two teams formed to conduct this study of the expansion history of the universe. One was led by Saul Perlmutter at Berkeley. I was initially a member of his team, but then I switched to Brian Schmidt's team just because of cultural reasons. This was a bunch of astronomers who were trained in the way that I was trained, and this was basically a bunch of high-energy physicists. And I have nothing against high-energy physicists, but the culture was different. We weren't always at each other's throats. It was generally a healthy competition. Both teams wanted to be first, so that accelerated progress in the field, pardon the pun. Both wanted to be best, so if one was taking something subtle into account and the other was not, then that other team would look bad by comparison. And frankly, had there not been two teams, other physicists and astrophysicists would not have believed the result of just one team because it was so outrageous. Both teams used telescopes primarily in Chile with wide-angle cameras that can take a picture of the sky roughly the area of the full moon, although I recognize the full moon is not rectangular. There are thousands of galaxies here. Repeat this picture and many others like it throughout the sky 3 weeks later, and you can see what has changed. Most things have not changed. So if you digitally subtract the first epoch from the second epoch, you'll get a bunch of noise. That's okay. Any measurement process necessarily has some noise associated with it. But here, cleverly placed near the center of the circle, is something that looks like it might be real. That's a supernova candidate. I then, as the spectroscopist on both teams, with access to the world's greatest optical telescopes, the 10-meter Keck telescopes in Hawaii, would take spectra of the supernova candidates, making sure they're the right kind of supernova, and I'll talk about those details tomorrow evening, and getting the redshifts of the host galaxies. So here is the punchline. Here are 3 supernovae. They look faint. Obviously, they're distant. And you might say, well, you know, yeah, fine, they're distant. They're in these pathetic-looking faint galaxies. Here you can't even see the galaxy. But my point is, these objects are more distant than they had any right to be in a well-behaved universe. And what do I mean by that? Well, they were fainter than they had any right to be. So the interpretation was that they were more distant. Well, what do I say, any right to be? Okay, suppose the universe is only 1 second old, and I toss the apple. I measure the distance of the apple from my hand after 1 second. It's some distance. But the apple has been slowing down due to the mutual gravitational attraction between Earth and the apple. So if Earth's mass were less, it would slow down less, and it would go a greater distance in 1 second. I can't make Earth's mass less, but I can do the next best thing, throw the apple faster, and it goes farther in 1 second. Imagine Earth isn't here at all, and forget about the sun and Jupiter and all that. Physics students know that I toss it, has no reason to slow down or change direction. That's Newton's first law. So it would get to an even greater distance if it were moving at a constant rate. Well, the point was that the apples, the supernovae, the galaxies in which they're located, are at a greater distance than the distance that was expected with no slowing down at all. So unless there's something going on, you know, fog in the way, or maybe the supernovae billions of years ago were not as luminous as today's headlights, we had to look into all that. I'll talk about it more tomorrow. The obvious interpretation is that there's a rocket attached to this thing, and it goes zoop like that and gets to a greater distance in 1 second. Now, you might say, well, there's an obvious flaw in your argument, Alex. What if the universe is 2 seconds old, not 1 second? Obviously, the distance will be greater. Good job if that's what you were thinking. All right, I can see the gears turning in the physics students' heads. Good job. But the argument in detail, which I will describe tomorrow evening, is independent of the assumed age of the universe. For a given redshift, the derived distances, the look-back times, were too great. So, an accelerating universe. Astronomers see a cosmic anti-gravity force at work, and I actually was privileged to be the first person on either team to announce this to the world in a meeting in Los Angeles in February of 1998. We use this term, anti-gravity, hesitantly, because people ask us, can we attach this stuff and levitate over Minneapolis, St. Paul, traffic jams or whatever? I don't know, are there traffic jams in St. Peter? Maybe? I don't know. Oh, okay. Well, anyway, regardless, no, you can't gather this stuff. It's either a property of space or it could be a substance filling space, but there's so little of it that you'd have to go out millions of light years, and so it's just not going to happen, right? Nevertheless, it is an anti-gravity-like thing. And, Einstein here looks kind of sad because he actually had proposed the possible existence of such an effect, not to give an accelerating universe, but to give a universe that's static, neither collapsing nor expanding. But he actually renounced the idea as having been the biggest blunder of his career when Hubble found that the universe isn't static after all. So here he is sad. He could have been famous if he had not introduced this idea of some sort of an anti-gravity, which he then renounced. Imagine what his surprise might be if you were to see the data. His idea was not a big blunder after all. It was maybe conceptually his greatest triumph in some ways. So that he looks kind of surprised there. But again, there's a lot of misunderstanding of this in pop culture. The universe. Actually, we should be glad as astronomers that we ever appear in pop culture and not be so worried about the details. But anyway, the universe is expanding at an accelerated rate. That should be good for housing starts. I don't think so, okay? And here's another one. The universe is expanding faster than ever, and I don't even feel a breeze. Again, not appropriate. It's expanding faster than ever over distances of at least 10 million light years. And by about 100 million, you start getting the full effect. Between 10 and 100, there's some other effects that mess up. So what could be causing this repulsion? Well, it could be the thing that was Einstein's original idea, which he called the cosmological constant, which would be a property of space itself. But it could also be some energy that fills space, like the light going through this room, but not the light, just something, like it. Not a property of space itself, but something that is just wandering around in space. So collectively, we call all these possibilities dark energy. And over the years, the picture for cosmology that has emerged from many different types of observations is that this is the cosmic pie. Averaged over large distances, it's 70% dark energy, and we don't know what it is. And 25% dark matter, this exotic kind, and we don't know what that is. Only 5% is ordinary matter. Only 0.5% is easily visible ordinary matter in the form of stars. That's what I was sort of alluding to earlier, that when I was a student, people knew about dark matter, but at least part of the stuff they called dark matter back then was just stuff that glows, but it hadn't been seen yet. That's now stuck in this part of the pie, the ordinary matter. So this is not your mother's universe, certainly not your grandmother's universe. This is really weird. And for the physics students here, if someone ever tells you, astrophysics is dead, there's nothing left to be discovered, you tell them, what about the origin and true physical nature of 95% of the universe, right? Not in this room. Again, you have to average over 100 million light years or more to get this pie. But still, that's what it is. Pretty amazing, right? So this is clearly pretty important stuff, right? This dark energy, huge mystery, probably the most important observationally motivated unsolved problem in all of physics today. 70% contents of the universe. It's a quantum effect almost certainly. It occurs on very small scales, but it occurs everywhere. So cumulatively, it dominates over 10 million light years. And so any unified quantum theory of gravity that rejects the possibility of an accelerating universe can be itself rejected as no longer being a viable contender for this theory of everything that theoretical physicists are trying to establish. This has already been used, by the way, to rule out certain varieties of string or superstring theory, though there are many, many more that are not ruled out by this observational constraint. That's the real problem with string theory, is that there are very few ways to test it, but at least this provides one test. So by this time, then, it got, was verified by a number of people and stuff, and was honored, the discovery was honored with the 2011 Nobel Prize in Physics, which went to the two team leaders, Perlmutter and Rees, and I'm proud to say went to my postdoc, Adam Rees, who, when we were working on Schmidt's team, was the first on Schmidt's team to realize what the data were trying to tell us. The first person on Perlmutter's team was arguably Gerson Goldhaber, who passed away in 2010. And it could be that the Nobel Committee waited until 2011 just so that one of the four principals dies. They just don't give it to more than 3 people. And it's crazy, especially that since big science now is done by increasingly big teams. The gravitational wave detection was 1,000 people. The Large Hadron Collider was roughly 8,000 people. Whatever. Anyway, these gentlemen understood that without the rest of us working hard in the trenches, the discovery would never have been made. And, it was really in honor of the discovery. Although, the prize is, the real prize was being part of this discovery. When I was a kid, I just wanted to contribute a little bit to humankind's understanding of nature. Never did I think I'd be so lucky as to be at the right place at the right time. But anyway, it was nice. So they spent their prize money, or a good fraction of it, flying out the rest of us to participate in Nobel Week, so that was a lot of fun. They put us up in the Grand Hotel. There are so many Swedes and Norwegians here in Minnesota that you probably even recognize some of the pictures that I'll be showing here, but here's the evening reception at the Royal Swedish Academy of Sciences, Supernova Cosmology Project team shot. I should have been in that picture, but at the same time, in a very busy week where we had very little free time, the main team with which I was associated was having its celebratory lunch, where my wife revealed her consolation prize for all of us, roughly 48, 50 people who did not technically win the Nobel Prize. It was a t-shirt, "Dark Energy is the New Black." And she sent this and a $2 bill to the King of Sweden saying, "Your Royal Highness," or however she referred to the King of Sweden, "here are 2 items you are unlikely to already have. This t-shirt, one of a kind, and a US $2 bill." She never received a reply, but that's because perhaps she sent the gift anonymously. That's what she does. Anyway, it was a whole bunch of parties and stuff, celebrations. Here's the symphony, the concert, fantastic. Lunch at the Australian embassy, since Schmidt is based in Australia. Here's the Nobel ceremony itself. Here's the Heisey team right after the awarding of the prize. Here's the banquet, which had like 1,300 people, but it was really hard to get a ticket. Even my wife didn't get a ticket, so I snuck her in afterwards so she could see the arrangement of the tables and stuff. And then there was an all-night party organized by the students in this really smoky room, and anyway. And then that was December 10th. We were all sleeping December 11th after this all-night party. And so then on December 12th, there was a symposium or a colloquium where it was sort of behind the scenes. Each of us could tell our own story and contribution to this discovery. So that was a lot of fun because the two teams got together. Anyway, and then there was this Nobel conference. Okay, so finally, in the last 5 or 7 minutes to allow time for questions, is dark energy really this thing that Einstein initially dreamed up, this so-called cosmological constant called lambda, which would be a property of space itself? Well, that's consistent with the data, but we're not sure. And by the way, you can see I had not yet received Danielle's photographs, okay? And then I forgot to hide this slide, but it's actually kind of funny that I still have it here because this is the penultimate version of this slide. But anyway, okay, so for years and years, it was pretty clear that the properties, the observed properties of the dark energy were consistent with the cosmological constant, but we weren't sure. And in particular, the density should change, the amount per unit volume should change if it's not the cosmological constant, okay? So that's the idea. So how can you address this question? Well, one way we've been doing that in the past, 24 years now since the discovery is trying to more and more accurately trace the expansion history. Go back in time and, we said that the universe is expanding now faster than it was 4 billion years ago. That's the statement we could make back in 1998. So since then, we've been measuring 1 billion years ago, 2, 3, 4, 5, 6, 7, 8, 9, 10, blah, 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 trying to trace out this curve. But that's hard to do, because minute differences in this curve could lead to rather different final outcomes. In particular, if the dark energy is constant in density, then it gradually dominates the universe, but it does not tear galaxies and clusters of galaxies apart because its strength per unit volume is not changing. However, it could, in principle, get stronger per unit volume. That it violates certain conservation laws in physics, but those are not God-given. They might be violatable. So this would rip clusters of galaxies apart, and then planetary systems, and then stars and planets, and us, and the very atoms of which you are made. The big rip, or you could call it the big rip-off, right? Or it's conceivable still that the dark energy could change sign in the future from gravitational repulsion to attraction. And if so, and if there's enough of it, we still could have the big crunch, okay? And it's these possibilities that were not completely recognized or not fully recognized in 2001. We thought, well, it's just the cosmological constant. We know what the universe will do. But we've been trying to measure what it did in the past and predict what it will do in the future. Okay, so those are hard measurements to make. Another thing to do, though, is to measure the slope of the line right now, and that's the current expansion rate. Measure the slope really carefully, and then slight differences will lead to potentially quite big differences. So that's a project that my former postdoc, Adam Rees, and I, and a team of us embarked on now nearly 16 years ago. And the most recent surprise, which just got accepted for publication, so this is brand new, should come out in print within the next few months, is that our measured current rate of expansion is higher than expected. Okay, higher than expected compared to what? Well, compared with predictions from early time observations. Now, what do I mean by that? Quickly, because I'm running out of time, radio astronomers can use telescopes to measure the afterglow of the Big Bang. It's radiation that fills space, all right? And it comes from a time when the universe was only 380,000 years old, because at earlier times the universe was opaque and the light scattered around too much, kind of like trying to go through the opaque sun or something like that. You can't look through the sun. It's opaque for the same reason. It's an ionized gas, okay? So here you see this, and there are these little freckles and stuff. And the size of these freckles, which correspond to temperature and density variations, the true physical size can be calculated in a fairly straightforward way. And then you measure the apparent angular size, and you do various things, and you use the standard model, okay, and propagate forward 13 billion years. In other words, since the data up to now have been consistent with constant dark energy, let that be the standard cosmological model. Take the early time observations, propagate forward, and predict the current expansion rate of the universe, the Hubble constant, or I like to call it the Hubble parameter because it changes with time, and so constant is a bit misleading. Okay, so, but we measured the current expansion rate very accurately, okay? And the surprising new result is the following. We measure this number, and don't worry about it, and don't worry about the units if they make no sense to you, but the point is 73.04 plus or minus 1.04. The prediction is 67.4 plus or minus 0.5. Those quite obviously disagree, and if you're pretty good at statistics, you can figure out that there's a conflict at the 5 standard deviation level. In high-energy particle physics, that's considered a discovery, because there's only one chance in 2 million that it's caused by a statistical fluke and is not telling you something real about the universe. It's like you're measuring raindrops in a square meter, and they're typically 100. So, you expect 2/3 of the time it'll be between 90 and 110, and 95% of the time it'll be between 80 and 120. If you measured 50, you'd think, maybe there's an umbrella over part of that square meter, right? Maybe there's something in the way that's affecting my result. Not just, it was just an unlikely statistical fluctuation. It could be, but it's very unlikely. So that's the idea. All right, and other independent methods now support our conclusion, but at a lower statistical significance, okay? But we're not the only ones anymore. So what's going on? Well, it's still possible that all the today's universe measurements are wrong, although, as I said, there are many methods now that basically come up with this number. So I doubt that we're wrong. And I doubt that the microwave background people are wrong. They've made their measurements in a very, very careful way. And there are a number of measurements relating to the early universe, which also all give the same 67.5 or so number. So let's reject this, although it's still possible. As a scientist, it's always possible you're wrong. So what are the possible conclusions? Well, general relativity, Einstein's theory of gravity, might be wrong. Physicists are enormously reluctant to come to this conclusion because general relativity, first of all, is so beautiful mathematically, physically well motivated, has many observational verifications, including GPS in small gravitational fields, and more recently, the gravitational wave detections. And then stay tuned on May 12th, the Event Horizon Telescope team, I think, is going to reveal their picture of the gas surrounding the supermassive black hole in the middle of our galaxy. So anyway, there's lots going for general relativity. I really doubt that that's the problem. Dark matter might be, behaving weirdly, interacting with light in some way, even though it's not supposed to, right? And that could be messing up our interpretation. Maybe dark energy is becoming stronger and we're all going to get ripped apart. There's other data that seem to not imply that, but it's still possible. Maybe there was an early form of dark energy that in a sense gave the universe a boost. It's like you're looking at a kid's soccer game and you see the soccer ball zoom by faster than any one kid could have kicked it. Well, maybe another kid kicked it first in the same direction, and that's why it's going faster. So that's a possibility, and this one is the one that's gaining some traction right now. Early dark energy before the formation of the cosmic microwave background radiation, okay? Or alternatively, but sort of equivalently in terms of its effect, if there's a new type of very light subatomic particle, some sort of a weird neutrino, that does not violate other things we know about neutrinos. It too could have given the universe a boost at early times. So we call this dark radiation to distinguish it from dark matter and dark energy. So who knows, stay tuned. This is a very exciting field. This is now rocking cosmology like nothing for, I'd say the most exciting thing easily in the last 10 years. Going back now to how the universe will end, we don't know, but if the dark energy is something like a constant density, like Einstein's cosmological constant, and if you want to see galaxies with your very own eyes with a telescope, come to one of the Gustavus, star parties, like the one we held last night, look through a telescope at a galaxy, and you'd better do it pretty soon in the next few tens of billions of years, because beyond that time, the galaxies will get whisked away to such great distances that they will no longer be visible, okay? But it's still conceivable that the dark energy will change sign and we'll have the big crunch, so we're not sure how the universe will end. Well, Robert Frost could not have known these possibilities when he wrote his famous poem, Fire and Ice, in 1923, but it's a remarkably appropriate poem given the subject material of this talk. Some say the world will end in fire. Some say in ice. From what I've tasted of desire, I hold with those who favor fire. But if it had to perish twice, I think I know enough of hate to say that for destruction, ice is also great and would suffice. So you see, Frost would prefer the Big Crunch universe ending in a passionate, hot, dense state. But if the universe and he had to perish twice, eternal expansion and an ending in ice would be okay with him. And that's perhaps appropriate given his name, Robert Frost. So I've been supported a lot in this research for decades now. We are being supported increasingly by individual families and foundations and companies. Sharon and Clark Winslow, in fact, until recently were residents of Minneapolis, St. Paul. But anyway, couldn't do this work without a lot of support. I'll be really happy to answer questions as long as Chuck would like me to. And then Chuck mentioned these video courses I've produced. Often when I give talks, 1 or 2 or 3 or 4 people will say, do you have anything I can sign and that I can buy? I brought a few copies of my textbook and my tapes. I'll bring a few more tomorrow. I don't want to go home with them. They're heavy. But anyway, I'll be happy to relieve myself of them if you would like them. But no pressure. Cash, check, Venmo, PayPal, or IOU. If you don't happen to have anything on you, no problem. I trust you. But anyway, they'll be over there, and I'll be over there after the Q&A is over. Okay, thank you very much. All right, I did it in only 5 minutes longer, which is only about 10%. So there we go.
Great. All right, thanks, Professor Filippenko. We will take questions. If you're online and you have a question, you can put it in the chat feature in YouTube. If you're not really on YouTube, but on the Gustavus website, you can click on the YouTube words at the bottom, and it'll take you to YouTube, and then you can join the chat from there. And we will collect questions and pass them forward from that. So does anybody have a question they want to start out with?
Great. I'll just, there's a microphone, or I can repeat the question as well. So either way.
Yeah. Is there any precedent for, I guess, cosmic forces changing over time, like you've suggested?
Yeah, that's a great question. Is there any precedent to these cosmic forces changing over time? There is, in fact. It turns out we think that our universe became really gigantic, vastly bigger than the parts we can see, through an early stage of the universe called inflation. In the first 10 trillionths of a trillionth of a trillionth of a second. So there was like a really strong form of dark energy pushing the universe apart, but then it stopped. It was like the launching of the apple, but then that energy transformed itself, we actually think, into normal matter, the stuff of which we are made, and antimatter and photons, but don't worry about that right now. But the point is, it turned it into the stuff of which you are now made. So you helped launch the Big Bang, in a sense, right? But that was very much of a repulsive thing, as I'll discuss tomorrow, something with negative pressure, which was not forever the same, not the cosmological constant. It was a dark energy type thing, which we call the inflaton, that which inflated the universe, that clearly changed into something else later on. So there's a historical precedent. Yeah, great question. That gives us some reason to be hopeful about some of these hypotheses of dark energy where it changes over time in a measurable way, you know. Yeah. Other questions? Gotta be questions. There's always questions, right? Yes. Okay. Jack, right? Jack. See, I got that from lunch.
For the various values of H naught that you guys were saying that you were disagreeing on between the two parties, you said yours was higher, right?
Yeah. So ours, for these various values of the Hubble parameter, ours is the higher one. So it's like the universe is expanding faster now, even when you take the known acceleration into account. That was already included here. So in other words, you might say, well, we discovered that the universe is expanding faster. You heard that 24 years ago, but we've taken that acceleration into account already. That's what the microwave background people did. And what we're measuring is too fast a rate, even having taken into account the acceleration that we discovered a quarter century ago.
So did Planck's, the one that Planck's telescope?
Yeah, the Planck telescope is simply one of many such measurements, but the best one.
Did that one support a universe that was just going to stop expanding, or was that one also in kind of in the same region?
Well,
expanding too fast?
the Hubble constant alone, right? It doesn't tell you anything about the future, okay? If taken just that number without the context of the overall curves and stuff. So what the Planck data did show us quite clearly is that on very large scales, the universe is not curved, flat, Euclidean. So gigantic triangles, not in the vicinity of black holes or neutron stars, but really giant triangles have the property that the sum of the interior angles is 180 degrees. And that you can get from the apparent size of these little fluctuations here. So that was a very useful thing. And in a sense, the microwave background measurements gave complementary evidence for this dark energy, because there were various other arguments suggesting that in the form of normal matter and dark matter, there's only 30% of what you need to make a flat universe. You'd get a saddle-shaped universe, a negative curvature universe, with only the stuff that makes up the normal and dark matter. So then they said, well, it's flat, so there's got to be some 70% of something else. What they couldn't tell was what that 70% is. Could it be some other form of dark matter, hot dark matter, or something like that? What we found with the supernova measurements is that whatever the 70% is, it's accelerating the universe. And moreover, we came up with our conclusion in 1998, a couple of years before the early generations of these kinds of measurements first showed that the universe is flat. But when they did do that a couple of years later, that was additional evidence that, yeah, there's 70% of something else, and maybe it's repulsive, although these measurements don't show that. The only clear measurements that show that are supernovae and other related measurements that can actually show an acceleration in the expansion rate. But the Planck data alone do not do that, and their Hubble constant does not do that either. Okay, does that make it sort of clear? And I'll talk again a little bit more about the details, tomorrow. But yeah, other questions? Don't be shy. Okay, Scott.
How does the James Webb telescope factor in?
Yeah. So how does the James Webb Space Telescope factor into this? By the way, it is so exciting, right? A year ago, I really doubted that we would have a working James Webb Space Telescope, because there were 350 plus potential single point failures, right? And with a 99% probability that any one of them will work, right? 1% failure rate. Well, 0.99 to the 350th power is a pretty small number. So I was pretty doubtful. And a few years ago there was a shake test and 100 screws fell out, but I'm told that 99 of them were associated with the same problem, so that's all they had to fix. But what if some screws were loose but hadn't completely fallen out during the shake test? But anyway, I was doubtful. Now, I'm, knock on wood, it looks like it's working. The remaining thing they're trying to do is, they've got all the segments, they can align them so they point at a star and all the images come together and give you a nice, image of the star. Now they are working on, when the telescope shifts from one star to another, to have that alignment process be more or less automatic, right? So you don't have to sit there fine-tuning it each time. So what will the James Webb do? So it'll clearly be of relevance for cosmology, especially in the area of galaxy formation and evolution. They will be looking at ultraviolet light that's been stretched to infrared wavelengths. In other words, very high redshift galaxies, the first stars and galaxies to be forming. That'll be great. Another very useful thing is they'll look at clouds of gas nearby that are forming planets and stars. Those clouds of gas often have lots of dust that blocks our visual view, but in the infrared, the dust is more transparent. And then finally, and this was unanticipated really at the time that the Webb was planned, there are now all these exoplanets that have been found, and some of them go exactly between us and the star that they're orbiting, which means that they transit, they block part of the star's light. Okay, so that just blocks 1% of the light. You might say, well, big deal. Well, the big deal is that there's also an atmosphere around some of these planets, and that light from the star can go through the atmosphere and certain wavelengths get absorbed depending on which atoms and molecules are in that atmosphere. So a big deal for the James Webb will be studying, I think, the atmospheric composition of exoplanets. For this work, it'll be, I would say, of limited utility, not zero, but it's a small field of view. So they're not going to be searching for supernovae, because for that you need large fields of view. But what it will do, hopefully, is take the supernovae that we find with ground-based surveys, with like the Vera Rubin telescope in Chile, that's nearly ready, slowed down by COVID, as were many projects, and then, look in detail at those supernovae. And in particular, I would think that we'll be looking at some of the highest redshift, most distant supernovae to track the influence of the dark energy over time. We think that initially it wasn't all that important because galaxies were close together, so gravity was attracting them quite a lot, and there wasn't much space between them, so the cumulative effects of the dark energy were small. So gravity would have dominated. But as the universe became bigger, first the distances became bigger, meaning that the gravitational attraction decreased with time, and the increasing volume of space meant that the cumulative effect of this dark energy became bigger. So in a sense, gravity is weakening with distance. The anti-gravity, if you will, is strengthening. About 4 billion years ago is when they crossed, and that's when the acceleration started. But if we look, 6, 7, 8, 9 billion years ago, we've done that already pretty well, and we can see the decelerating phase of our universe. But with the Webb, we should be able to do those measurements much more accurately. So that's what I think it'll do. But honestly, I think the main impact of the Webb will be in the 3 areas that I first mentioned, and not so much enlightening us as to the true nature of dark energy. I think it may play some role in that, but not as big a role as some other telescopes. So, yeah. But it's really exciting, and, just another NASA triumph, really, Other questions? Yes? What happens at the end of a black hole's life? Oh, is that the question you asked? Okay, so that's a very interesting question, because if the universe recollapses, then there's no time for the black holes to do anything other than sit there, mostly absorbing stuff that's in their vicinity, including the cosmic microwave background radiation if there's no nearby stars and stuff. But let's say the universe expands forever. Then a very interesting new process will dominate someday, some year, 10 to the many large number, exponent years in the future. and that is the evaporation, the quantum evaporation of black holes. Hawking predicted, and it's not been observed yet, but it's a fairly generic prediction of any reasonable sounding quantum theory of gravity, that black holes should be able to evaporate. And it's a weird process. You can think of it as sort of tunneling. I could bash myself against this wall, and if I were to do it long enough, one of these days I would end up on the other side unscathed. I'm not going to do that because most times I would end up being a bloody mess, okay? But little tiny particles can do it more easily, and so they can escape, all right? And that's one way of looking at Hawking evaporation. There's a number of ways. All known black holes right now are swallowing material at a much faster rate than they're evaporating, okay? And you need to get to kind of little microscopic black holes before you notice the evaporation to be very strong. But if the universe lasts an infinite amount of time, even today's big black holes will someday have no more stars to ingest. Even the cosmic microwave background will be of such low intensity that the rate they ingest will become smaller than the rate at which they evaporate. And then they will ultimately explode because the rate of evaporation increases as the mass actually decreases. So it's the microscopic black holes that go off with a bang. The problem for Hawking is that no such bangs were seen. Initially, it was thought that a phenomenon known as a gamma ray burst might be Hawking's evaporating black holes, but further studies showed that the observed properties of gamma ray bursts simply did not agree with Hawking's predictions, and now we have very good hypotheses as to what they really are. They actually mark the formation or growth of black holes, not the evaporation of black holes. But the fate of a black hole ultimately is to evaporate, giving just radiation, a few little particles. Most of them meet up with their antiparticle partner and produce electromagnetic waves. A few might not. You know, the universe will become very empty, very cold, not absolute zero, it turns out, for a technical reason, and very, very dilute, okay? Sort of, you know, I mean, kind of a, I don't know what you consider to be a more depressing ending for the universe, that or the big crunch. Either way, it's not great for human existence, but we're talking about minimum of 100 billion years, if not trillions of years into the future, you know. So I wouldn't worry about it before next week's or this week's final exams, you know. Yeah, Steve.
We got an online question.
Oh, great, super.
It says, is it possible that the speed of light was different? In other words, faster early in the formation of the universe? than
Yeah.
now?
Yeah, great question. Is it possible that the speed of light was different early in the history of the universe, and that could even be fooling us into thinking that the universe is accelerating? So let me answer that in two parts. First part, no. Out to the distances, the look-back times over which we've looked, and the original conclusion was based on look-back times of 4 or 5 billion years. We have even laboratory measurements of the speed of light, which are very, very precise over a very short time, but the precision is like a part in 10 to the 16 or something like that, and so you can figure out that over a billion years, that wouldn't have been enough to alter our results. Moreover, there are other measurements of things like fundamental quantities in physics, one in particular called the fine structure constant, which dictates the separation of the energy levels in atoms. It's the square of the electric charge divided by Planck's constant, divided by 2 pi, but who cares, divided by the speed of light. So by looking at lines, transitions in atoms very, very far away, we can see that their electronic transitions are the same as in laboratory gases. So that means the fine structure constant has not changed. It either means that none of the constants, E, Planck's constant, or the speed of light are changing, or much less likely, they're all changing in just such a way as to keep the fine structure constant the same. Possible, but extremely unlikely. And there are other combinations of constants which you can argue, you know, in the individual ones are what's remaining constant and not just their combinations. Okay. However, if you go far enough back in time, yes, the speed of light and the fine structure constant and things like that could have changed. Indeed, we think that, and you know, we actually already know from particle type experiments that at really high energies, when you collide particles together, the various forces of nature get kind of unified. In particular, electromagnetism and the weak nuclear force have been shown in laboratory experiments to be essentially one and the same. They're like the analogy I give in my class. You have a quarter and you spin it on the floor and it's the spinning quarter. It's neither heads nor tails, or it's both, whatever you want to call it. And gradually it spins down and it lands heads or tails. Those are two manifestations at low energy of a fundamentally symmetric unified spinning quarter. All right? So there's electroweak. And then we think the strong nuclear force is unified as well, and maybe even gravity. So in those cases, the so-called coupling constants, the constants that kind of tell you what the strengths of these forces are, they are thought to unify long, long ago when the universe was very, very young. But now we're talking about tiny fractions of a second, and so those are irrelevant for the 4 billion years that we're looking back in time out of 13 or 14 billion. So over the time scales over which we made the measurements that led to this conclusion, the speed of light is not changing, but the constants of nature could well have changed in the earliest fractions of a second of the universe's existence. Absolutely. Yeah, great question. Yeah, yeah. Are there any other online there? Okay. Okay, well, thank you so much. And again, if you have a question you'd ask me privately or whatever, I'll be down here. And thank you for your attention. Great. And let me thank the Rydell family for sponsoring this almost 30 years ago now. Next year, it'll be your 30th anniversary, so thank you very much. Yeah, great. All right.
Turn off the microphone at some point.
Yeah, right, right, yeah. Very good.
Good job.
Thank you very much, yeah.